Recording in
Okay, good morning, class. Can you guys hear?
Yeah, good morning, sir.
Good morning, sir.
Morning, sir.
Hope you guys had a good semester break. All right. So today, as promised, we're going to be covering Simulink. Everyone downloaded MATLAB, right, with Simulink?
Sir, I was unable to download it because the computer that I'm using only has 58 gig of RAM, 58 gig storage, sir, and half of it is used up by apps that come with the computer. And when I checked the app, it was about 17 gigs to download it, and my computer only has about 17 free, and it cannot download, sir.
Okay. All right. So we'll find a solution for that. Okay. All right. So Simulink is just, as the name suggests, a simulation link for MATLAB. So as you might have noticed, that MATLAB, even though it's very capable, sometimes you want a little additional support. You might want to simulate things in more of a systematic way, right? In a graphical flow way. So Simulink is essentially a product or and like an extension of MATLAB that helps us do certain things like that, right? So instead of typing code all the time to simulate every single part of our system, we can use Simulink to drag and drop these things that are called blocks, right? These blocks to help simplify our code or make our life easier, because in certain fields, there are certain things that are similar that we might always want to do. Okay. So in order to launch Simulink, there are two ways. One way is you type Simulink here, right in the command window. You press enter, and it should start launching. Let me cancel that. The other way is to come up right here, where Simulink is, and click it. And it'll start launching. It should take about a minute. Yeah, good. So here is a Simulink start page, which most of you should see, unless you have some other default setup. Right? And from here, we can just open up a blank model, or if you know what you're doing, you can go ahead and do like different kinds of templates, right? And you can create your own templates as you progress and as you use Simulink more. Now, in this other tab, there are some examples. And these examples are from many different fields, right? And these are just different things that show you how you can use Simulink, right? So let's just open up an example and play around with it. Okay. This here is the model of a bouncing ball. So first thing you might ask yourself is, where's the ball? Where's the ground? Why isn't it bouncing? Well, Simulink isn't that kind of simulation software, right? As I've said before, if you want the kind of animated simulation that you would see in like a movie or simulations with a lot of graphics, right? Simulink isn't a tool for you. You'd want to look into something that does 3D animation, something like from the Autodesk kind of software. This here focuses more on the functions, the mathematics, right? The numbers and the graphs and stuff. That's the purpose of Simulink, because we want the numbers. We don't really care about how it looks. We know how these things look. We want the numbers, right? We want a tool that can crunch numbers for us. So if you run the simulation, and of course, this is just some example within the thing. You see, we can use it to generate certain graphs, right? And this here is a graph of the position of the ball throughout time, right? The position of the ball throughout time. So you see, it would, as we first drop it and we start reading, it would be bouncing, right? come down, bounce back up, come down, bounce back up, come down, bounce back up, till it kind of tapers off and then does nothing, right? And here's just a map of the velocity. So with Simulink, we can create models, right, based on certain things, models of our system, and use them to generate graphs and other useful things. And of course, we can generate numbers like specific variables, like the answer to a particular question, whether it's 5 meters per second or 12 volts or whatever, and send as the output and put it back into our MATLAB program and then do some other code, write some other code to work with that, right? So now on your own time, you can of course run through all the different examples they got. They're way more than this, so you can look at all of them if you want, right? In your own time, right? But for now, let's just open up a blank model. And you guys can follow along with me on your own computers if you have Simulink installed. Okay, so this is a blank model. As you can see, there's nothing on the screen, right? Nothing at all. Okay. So now what we want to do is first think of something to design. We'll start off with something simple, which is we're gonna try modeling the square wave, right? But as a sum of sines and cosines, with something you guys probably vaguely remember from our Fourier series program, right? So here, in the upper left is the library browser. Now in this library browser, there are a lot of different pathways, right? A lot of different pathways. Your Simulink pathway with all of the commonly used blocks. Now these are blocks that you use in all different types of blocks that are used in all different types of engineering, all different fields, whether it's robotics or just fluid mechanics or anything like that. We'll always be using some basic things like, okay, we send a signal in, what is the integral of that signal? So we can use Simulink to actually do some math, right? We can send a signal in and out will come the integral of that signal, right? And of course, we can use it to do differentiation as well. We might want to use something like a scope so that we can see what the signal looks like, right? We don't just want to differentiate a wave. We want to see what the derivative of that wave looks like, right? We might want to use some logical operators, right? Something like if both of these things are true, then do this, right? And all sorts of other things. And of course, the continuous blocks, right? For continuous wave signals and discrete blocks for discrete wave signals. I think you guys know the difference between those. Let me just get my pen up. Okay, so something unrelated is continuous waves or continuous signals, which you will learn more about as you progress in your engineering life, and discrete signals. So a continuous signal is one where it's continuous, right? So let's say we have a sine wave and it flows continuously, right? So at any point in time between, let's say 0 to 2 pi, we know what this value is, right? We know what the value of sine is. We can go and we can pick out the value of sine. Now for a discrete signal, that's a bit different, right? At any point, let's say this same sine wave, but discretized, would look something like this. This is just how we graph it out. Right? This is how it looks. So the signal isn't exactly available at every single point in time. But what we have is different samples, right? At t equals 0.1, we have a value for this sine wave. At t equal 90 or something, we have a particular value, right? We only have a certain set number of values, certain number of discrete values for a signal. So for almost every block, you'll find there's a continuous version and then there's a discrete version based on what type of signal you're using. Okay? Because in the real world, we're not able to collect continuous signals all the time, right? Sometimes we might just be able to sample, right? Sample, take a sample of wind speed here, a sample of wind speed again tomorrow, a sample of wind speed again another time, and so on and so forth, right? And we can use that to generate data, and we can operate on that data. Okay, good. And of course, if you install some additional packages, let's say, for example, an HDL coder, HDL stands for Hardware Description Language. And this is something that we would use with things like FPGAs that we can use to program the FPGA to become a microcontroller or to become a small microprocessor, right? It's used in the design of digital electronics, and there's certain blocks related to that, right? And you can expand it under the commonly used HDL blocks, right? And there's something like logical and bit operations, right? So things like bit slice, bit shift, which are all things that are used in this particular field, right? HDL RAMs, which is read-only memory, and different ports. So we can use this to design computer systems. Now, if you had something else installed, maybe something like fluid mechanics, robotics, you'll have a section here that you can go in and you'll see all sorts of different blocks that will help you to model robotic systems, right? And of course, you can't expect the same kind of, those kind of highly animated simulations that you would see online or anywhere else. That's something that you want to do with some animation software and not with Simulink. So let's start on today's exercise, right? The Fourier series, quick review. The Fourier series says that any signal based on some sort of parameter, some sort of prerequisite criteria can be broken up into a sum of orthogonal signals, right? Or for the trigonometric version, into a sum of sines and cosines. So a wave like the square wave, right, can be broken up into some sines and cosines, right, of different frequencies. And if when we sum them up, we should get back the square wave, right? Of course, we would need to sum up to infinity, right? To infinity. So let's take a look at the math for that. So the square wave, as we know, it follows a weird Fourier series formula, right? Which is very long, complicated. And then we need to solve for an and bn and a0, right? And in solving for an, bn, and a0, we found that a0 is 0, an is 0 for all of them, bn is 0 when n is even, and bn is 4h upon n pi when n is odd. So we end up with this kind of expression, sine x plus sine 3x over 3 plus sine 5x over 5, and so on and so forth. Because it's a summation, right? It's a summation, but we expand it, and these parts are equal to 0. So we kind of only left with the sine version. And of course, eventually you guys will learn math about how to do that. But firstly, we have the square wave, and we know first, its first component is sine of x. So we need, in Simulink, we need to bring out this sine function. Okay, so this is Simulink here. Now we can go in a library browser, right? And we can go to commonly used blocks, and we can fiddle around right? We can go to sources, we can fiddle around, and maybe if we're lucky, we might find this sine block, right? And we say, okay, this is what I need, right? This is what I need, and then we can click on it and drag it out. This is too big. Yeah, we can click on it and we can drag it out, and we have this sine wave here in our program. Alternatively, what we can do is double click here, and you'll see a little search window pop up, and in there we can type sine, right? And we can see sine wave or sine lookup, sine wave function from all sorts of different places. Where we want this from is from sources. So sine wave from sources, go ahead and click that, and then the sine wave block will pop out. Good. Now we also want to view this sine wave, right? So we want something like a scope, something that we can view the sine wave with, right? So let's go ahead and get a scope. So we can double click again and type scope, or you can go into your library browser and look for a scope, right? So a scope would be a sink, and there's a scope here, and you can drag that out. Okay. Scope. So scope's here, sine wave's here, and we can click this little button here to just zoom in a little bit, but zoom in to the extent of where all our blocks are, right? If you had more blocks, it wouldn't zoom in this close, right? Now we need to connect these two items so that we send the sine wave into the scope, right? And you can see little arrows already generated, and you can click on that blue arrow, and it'll generate some line connecting these two together, right? Now we can define the parameters of the sine wave, right? We can design the amplitude of the sine wave, the frequency of the sine wave, right? And so on and so forth. So if we go ahead and click run, then we click on scope, we see the sine wave is here, right? Simple, nothing fancy about it. So let's go ahead and slide that scope there. Slide this one here, go back to extents. So we can see side by side as we change, as we update. Let's change the amplitude to 2. So right now the amplitude is at 1. We're changing the amplitude of the sine wave to 2. Now we know what that does is essentially moves from something like sine of x to 2 sine of x. So that when sine of x is 0 and is equal to 1, it's 2 by 1, right? Which is equal to 2. Instead of here, where it would be 1 by 1, which is equal to 1, right? That just changes the different coefficients inside. And you can do phase shifts and frequency. I mean, the frequency is kind of like putting an n there and changing that n, upping the frequency, right? Yeah. So we change the amplitude to 2. And the scope is here, but our scope hasn't changed. Well, why? Because we need to refresh the simulation. We need to refresh all the numbers in the simulation. We need to run it with the new parameters inside, right? So run again. Now, what we should notice is that it runs and it stops. It starts at 0 and it stops at 10 seconds. This is based on this parameter here, right? Now, because we don't have all day to run a simulation, right? We will want to run it for a fixed amount of time, right? For that bouncing ball, we might not want to wait until that ball bounces up, comes back down, bounces up, comes back down, bounces up, come back down, bounces up, come back down, right? And then all this little jittering at the bottom to go away, we might not want to wait all the time. We just want to know what's the position at maybe 5 seconds, right? So we can run the simulation for like just the first 6 seconds and then pull off that point at 5 seconds, right? We don't need to run the entire simulation for forever until it's done or something. So we can set how long we want to run the simulation for. This saves time. Okay, so we run the simulation again, and we see the sine, the amplitude changes to 2. So we can modify the amplitude. And we can also modify the frequency, right? So the frequency, let's change it to 3 rads per second. And then we run again, and we see there are more peaks of the sine function. Now, what you might also notice is that these ends are a bit jagged. Okay, these ends are a bit jagged, and that's just the resolution of what Simulink is using, right? It's just the resolution, because not every computer has unlimited processing power. So to process all of these different points might take a lot. So Simulink allows us to control how much processing power we put into defining these functions, right? Some functions you might not worry about them a lot. And this here would be a close enough representation of the sine values that you want, right? You wouldn't really care about these small little errors. But in case you do, you can go ahead and change that as well, right? So same way, when we were plotting our sine wave, we do -10 to 10, and we get some kind of jaggedy thing. Then we put the other colon, and then we do 0.1 intervals or whatever, 0.01 intervals. It's kind of the same thing like that, right? We need to set the resolution a little bit. So we can come into modeling, right? Expand this a little bit. You come into modeling, then you go modeling settings, right? Model settings. Let it load. Okay. Then you can set the details in the solver, right? So the max step size right now is at auto, but we don't want that auto. We want something with bigger resolution, because right now with auto, we've seen these jaggedy things, right? So we don't want that. We wanted something like maybe 0.1. Seems like a good setting to have. Let's try it out. Simulation, run again. Right. Let's look at our scope. A little bit better, but not the best. We could go a little higher in resolution, right? And if you guys can see, but there's still little cut off here and there, right? Still little issues. So you come back to here, and maybe we can go 0.01, right? And this here is 0.01 seconds or milliseconds, right? Because remember, everything is in time. So in running the simulation, every 0.01 seconds is going to take a sample of what these functions should be, right? Of what our system, what all the values in our system are supposed to be. Once again. And now we see our wave is very smooth, like even at the top here, very smooth for all 10 seconds. Good. So we got a sine wave out, we figure out a good resolution. So we're progressing. All right, good. Good. Now to copy a block, let me delete this line. Now to copy a block, how we can do that is right click on it and drag it downwards, right? Right click, and it should copy, oh, sorry. Close this. Okay. So we right click on the block and we drag it downwards, right? And it should go ahead and copy the block, right? So now we have 3 sine waves, because we want to do a certain amount of sine waves to represent this square wave function, right? As we add more sine waves with, of course, different frequencies and different amplitudes, we get different results, right? Okay, good. So for the first sine wave, the amplitude should be 1. The frequency should be 1. course, we can change the amplitude to something else. Now for the second sine wave, the amplitude needs to be 1 divided by 3, right? And the frequency needs to be 3. Now, what we also need to do is sum up these two signals, right? Sum up these two signals. So we need a block that sums signals. Right? So this is a sum block. It sums signals. So we can put two signals into that block, and it'll add them up, right? So the same mathematical operation we would do, sine x plus sine 3 of x, sine of 3x divided by 3, right? Plus sine of 5x divided by 5, of course, is infinite summation, right? We can do that using the sum block. Of course, we need to add more inputs to the sum block, but we'll come to that, right, a bit later. Now, if you want to label your sine waves, you can go ahead, click on it, and then this blue thing will appear at the bottom. Now you can click on that, and you can say sine wave 1, right? And then it'll go black. And then this one here, you can say sine wave 2. And this one here, sine wave 3. And little things like these, how to label and stuff will come about.
Excuse me, sir, repeat that again.
Yeah, to label them, you just click on the block. Let's say the scope. You click on the scope, this little blue part is going to come up, right? So you see this little blue part here with the label. You can click on that, and then you can type scope or just scope, right? Scope 1, and it'll show up. Now, another thing is when you click on the scope, or let's say click on summer, these little 3 dots are gonna appear on top. 3 dots right there. So you can click on those 3 dots, and you can say hide block name, right? See the block name disappears, and show block name, and the block name comes up, right? So you can do things like there. There's also comment out. So let's say there's a block that you don't want to be used anymore. You can comment it out, and it kind of grays out. The same way you would comment out code in MATLAB, right? It turns it off. So just click here, show block name if you want, or hide block name. And you can just click on the blue thing and type in what you want to name it. Sine wave 1, 2, 3, 4, right? Okay, you get it now? How to label?
Yes, sir.
Good. So that's just labeling. And remember, this summer is the sum of these two sine waves. So sine wave 1 has these parameters, frequency 1, amplitude 1. Sine wave 2 has these parameters, frequency 1/3, amplitude 1/3, frequency 3. And then we want to look at what our signal is going to look like, right? Got the zoom thing in my head. Okay, so let's look at what our signal is going to look like. Let's run it. Look at the scope, right? Now we see it kind of starting to look like that square wave, right? Now it's only one of them we added up. And remember, this thing needs to go to infinity to look anything close to a square wave, right? But we can still go ahead and keep adding, right? So this plus this should give us something like this, right? And then our next sine wave, which is sine 5x over 5, like this, should give us something a bit closer. And as we keep adding, you'll get more and more to this square wave, right? A better approximation. So let's go ahead and keep adding. And let's copy some more sine waves, right? Now you can see there's some auto set things, right? Like the distance in between them, right? And if you were to move this around, you'll kind of route the cornering straighten up. So there are just some lines that appear so we can keep everything level and organized, right? So like this summer would line up with this scope here with that blue line there. And you can line up to the center or to the middle, to the end. So you can keep everything a bit neat. If you like OCD a little bit, and you just want to keep everything neat. Right. So now we need we need an extra input for a summer. So you can go ahead and click on this summer and click properties. Like double click on summer. Okay. And we see the block parameters, right? So now the list of signs, right? You can go ahead and add another plus sign to there and click apply. And now we see another input comes there, right? Another plus sign. Same thing with this. Okay. And for scope, let's set the number of input ports to 3. Did I accidentally close? Okay, good. So I just did 2 things there. One is I changed the number of inputs for the summer. So just double click on the summer or right click block parameters here. Double click on it and the list of signs, just go ahead, go in here and add a plus sign. If you wanted to do subtraction, right, you could change one of these to minus, right? And you can add two signals and then subtract 1. So you see here, let me zoom in. See here, a minus sign appears there. So we just alternate the list of signs. Okay? So put a plus sign. So now we got 3 inputs. And we can move it around again, line everything up. Line our scope up, right? Keep everything neat. And now we need this third wave here. And we need to set the parameters, of course, right? So this wave, the amplitude is 1 divided by 5, right? And the frequency is 5. Apply. So let's just have a look at this wave. In a scope alone, without summing it. So this here is the new wave, right? 1/5. And this here is the old wave, right? The old wave. Now let's go ahead and add this new sine 5 into the old wave, which is the sum of those 2. Alternatively, we can put another summer here and just have different outputs from a scope for different steps along the way so we can see how they change. But we enable add so many summers and have so many things, right? So we can just click here and join it up to this path. And then the third sine wave is going to be add into the summer, right? Which will of course change the output. Then we need to run the simulation. And we see it's a bit better now, right? So from adding this blue wave here, we see the simulation is a bit better. Let's delete this. Let's delete the summer. Let's delete these lines. Let's add 2 summers. Summer for these 2. And then let's add another summer. Sum that plus this wave here. And we take this signal. Okay, good. So I did a thing, right? Instead of adding all 3 of them up, what I did is I add 2 of them up, then I want to take that into my scope. Then I add another summer to add 3 of them up. So we'll take those 2 that are already added up and we'll add this 5th one. So we just put the intermediate summer so that we can see the difference between the different stages, right? As we add the different levels of sine waves. Let's run. Okay. Now we see our first sine wave was this yellow one, right? Which was there. And we see our second sine wave had more peaks, right? Had more peaks, which is a bit nicer. So this sine wave, sine wave of frequency 5, amplitude 1/5, helped us improve our model of the square wave, right? Now we can keep adding more blocks, right? The next block should be amplitude 1/7, frequency 7, apply. Let's change this to 3 now. Put a plus sign, apply. Get that sine wave there. Send this sine wave in here. So we're kind of doing the same thing. And we want to look at this new sine wave as well. So we're adding in this 4th sine wave. We're joining the 3 of them up now. So the 3 of them would now be the old signal. Right? And this 4th one would now be the new signal. So you can go ahead and run that. The scope. Now we can see the yellow one with 3 peaks now is the old signal, and this blue one with 4 peaks is the new signal. So we see a way of kind of slowly getting better as we add more sine waves and go ahead and add as much as we want, as much time as we have to waste, right? You can go ahead and do that. Right? But the thing is, right, is that because of Simulink, we're allowed to stop along the way, right? Different points like here, right? We can view all the individual sine waves. We could view different points in time, like before we sum the 4th one, we could view here, right? We could view the original and we could view the sum of all 4, all in our scope. So we can analyze data at different points in time, So if we had some really complicated system, right, that needed to use a lot of really complicated blocks, right? We can look at data at different points in time, right? Of course, we don't always need to use a scope because not everything is a function, right? We could use a display. Yeah, we can use a display. Let me just drag this out here. Use a display. Right? And we could use a constant, right? You guys know what constants are. Constants are basically just numbers. So even if we were just doing like basic arithmetic, we were just adding a bunch of numbers together, right? 3. We could display those values out onto our display, right? You see the value here pop up. So in between here, if there was any kind of calculations going on, we could look at different values along the way, right? We don't only need the end result. So that's the kind of modular ability Simulink offers us, okay? So if you guys haven't done this scope setup along with me, take a few minutes, try it out. I'll leave the math here. If you want to see it, you can just ask, right? This is the function. Let me just copy it.
So I got some questions, sir.
Okay, go ahead.
All right, good. So the sine waves, right? Those 4 sine waves, are they all at the same value?
No. So remember, we're changing parameters. We came in, we changed the amplitude, we changed the frequency. Here we came in, we changed the amplitude, we changed the frequency, right? Here we came in, we changed the amplitude, we changed the frequency. Here, we also changed the amplitude, we changed the frequency, right? So this here first one's a regular sine wave. When we add that to this sine wave that we did a frequency and amplitude scaling to, right? We would get something like this, right? So here, this one is like that. This one is like that, right? A bit smaller, but more peaks. Should give us something like this. And then this one added to this, right? The sum of those two. Again, it's a bit smaller, but more peaks, right? Will give us this, and so on and so forth, adding up to the perfect square wave. If we were to go to infinity, or if we were to go to somewhere like 100, we get close enough representation of what a square wave is. Okay? Does that answer your question?
Yeah, it does. So let me get the values for each of those different four waves you gotta set for
Okay.
the different sine waves.
Good. Okay, they're right here, right? They're sine of x, sine 3x divided by 3, right? So the amplitude is going to be 1/3. And sine 5x divided by 5, so the amplitude is going to be 1/5, and so on and so forth, right? So it's the odd numbers. So the first one, the parameters are here. I don't know
Yeah, so
how I-
the sine x, what would you put inside when you go to parameters? Would you just put one?
Yeah, 1, amplitude 1,
One for
frequency.
amplitude, frequency one.
Yeah.
Good. But for sine 3 of x divided by 3 now, sir.
The
Let me get
frequency is 3, the amplitude is
Mhm.
1/3.
Amplitude
Right?
is 1/3.
So for a sine function, right, let's say
Sir, I
a
could assume the
sine
third one would be the amplitude would be 5 and the amplitude would be
1
5
upon
over
5.
1 upon 5 and the
This n here denotes the
5.
frequency, and this here denotes the amplitude, right? Okay. So here is actually 1 upon that thing, right? So like a would have to be 1/3 to get like division by 3, right? Basic math. You guys understand this. So with you guys want me to leave up the Simulink model here, or you guys want me to leave up the function? Maybe I can do both.
Excuse, sir.
Yeah, go ahead.
Yeah, I got two questions, sir. In Simulink, right? Remember you said something about the
1
processing
second, please.
speed.
1 second. Yeah, go ahead.
Yes, sir. You mentioned something about processing speed, and you went over to the model and changed something that caused the function to be more defined. I didn't get to see where you changed. You could please just run back this step, please.
Okay, good. So you come in modeling here, modeling, and then you go model settings, right? And then you click on model settings, and a big window is going to pop up. And you first is here's going to be, it's not going to be there, right? You're going to click on the solver. Here's going to be collapsed, right? So then you need to click on this little thing here to load up here. And then you want to change max step size to 0.01, right? 0.01. There are a lot of things in here. And as you progress with Simulink, you might learn about them, you might not, right? But change this max step size to 0.01, and that should fix all the issues you have with resolution of these particular sine waves.
All right, thanks, sir. The other question was with the scope, sir. I didn't see how you got it to accept 3 inputs.
Okay, good. So for the summer, you did double click on the summer and you add in a sine, right? For the scope, you need the scope parameters, right? So block parameters here. And it kind of just opens up the scope. So we need to do is come into think file, number of input ports, and change that to 3. Right?
All right, thanks, sir.
Yeah. Okay, so look, I added the equation at the top here, right? So here, from here, it would be 7, 9, 11, and so on and so forth, right? And I can delete this constant thing here. That we have here. And remember, you guys don't need to do both summers. You can just do one with 4 inputs, right? You don't need to do the intermediate step, right? Any questions? I'm right here. Just ask. Simulink model.
Sir, straight up to 39, not gonna give you a the perfect sine wave still, a good sine wave.
No, don't go all the way up to 39, right?
Oh, yes,
Sir.
sir.
Sir,
Yeah, go ahead.
how do you add components in this thing again?
This summer, so double click, type sum.
No,
Click
like
on
how
that.
did you bring in this sine wave? We have to go to put it on. The Simulink take long for load up. It just load up for me, sir.
What do you mean? Put it, so you click here, and then you click there, and it's draw a line.
How did you get it in? Did you click create subsystem at
Oh, blank model, right?
and after the
Blank model, then you click here, you double click in the middle,
double click?
and then you type sine, and you pull the
Oh.
one from Simulink sources, right? The sine wave. Yeah, Billy. So you're trying to run, but it's not running. So does it not load up, Simulink?
Yeah, it's not loading up. You want me to share my screen?
It's take long for load up. You got
Is it taking a while or
yeah,
Not
it's
taking
so
a while. It's just blinking and.
not loading?
Mhm.
Sir, you're right. On drag, it isn't working for me. So,
Right
copy
click
them.
and
I
drag.
have to copy and paste.
Okay, well, copy and paste, but you should be able to right click and drag, right?
I wasn't able to do that.
And then notice that it also labels them automatically. It's 5 and 6, so they're labeled automatically.
sir.
Yeah,
I type in sine and I get a blocker. I get sine u open bracket 2 times pi times u. Where's the
sine wave. Did you click here? No, not the sine wave from sources, not lookup tables. Sources. Right, so sine wave, not sine. Right, sine wave. So
You have to click on sine wave or sine?
sine wave.
Okay.
When you type sine wave. Okay, better way to get it is come library browser here. Click on library browser. Click on sources and this sine wave in sources, right? Simulink, sources, sine wave. That's sine wave we're looking at, right? I was just doing this, right? Sine. Okay, it's good. So don't go all the way up to 39. You can stop anywhere around here. It's fine, like 7 or 9. So just practice. Remember, try and keep everything neat if you want. Okay?
How far you gotta go before it start getting straight?
What do you mean straight?
you didn't say it was
The sine
infinite?
wave, the top of it. I got a far one, but it still didn't get straight.
You did 41 sine waves.
No, sir, 20 sine waves. But the last odd number is for the one.
Okay.
I think it's straight.
Yeah, it's not gonna get straight, but it kind of gets let me see. It should keep getting better and better though, right?
Yes, sir, getting better.
Yeah, remember for a series, for it to get perfectly straight, it would have to be somewhere around infinity. right? For it to be perfect. But at like around 100, right, it'll be close enough, right? The square waves we use in life generally aren't perfect square waves either, right? Things aren't ideal. So this here would be a good enough model. And the thing is, if you were to break down a square wave like this, you wouldn't do it in this way. This is just to give you guys a little insight into Simulink, have you dragging some components, playing around a little bit, copying some stuff, labeling some stuff, using a scope, adding some functions, right? If you want to use a square wave in Simulink, you could even do Fourier analysis with Simulink. I'm sure there's a Fourier analysis block somewhere to do specific Fourier analysis things, right? Yeah. And there somewhere in here, I'm sure there's a square wave function, right? There's this pulse generator here. Right, so let me delete this here, delete this here.
Wait, so we no longer use scope?
No, you guys keep building, right? When everyone's finished with the.
So how long did it take you to learn all of this?
The thing is, there's no like you don't stop learning, you just keep getting better, right? Okay. So you guys are first year engineers, like you're not gonna know everything, and I don't expect you to know everything, right? I finished my degree, I worked for a few years, I teach, and I still don't know everything. The thing is, you keep learning, right? You know, and the thing, nothing is really hard, but sometimes you can look back and be like, wow, I learned a lot, right? So as you progress, right, you're gonna learn little by little, right? Little by little, right? And you're just gonna keep building. Right? But right now, you guys are somewhere around here. But eventually, in a few years, some student, some person you're working with, gonna look back and be like, "How you learned all of this? How you learned all this? How you learned all this stuff, right?" But you started from here, and then you slowly progress, right? It's a progression. You're not gonna learn everything in one day, right? But you're gonna slowly build and build and build and get better. So it takes time, right? One day you're gonna look back and realize, oh, I know all these random stuff. Okay.
So where did you get the scope from in the library?
Just type scope. It should be in sinks, right? Sinks. So that's another bit of terminology as well. So a source is a familiar word, something like voltage, supply, right? Voltage source, right? Something comes from this, comes from source, right? A sink is the opposite of a source. So this would be like a load, right? It's something like a heat sink, right? Heat comes from your components, and then your heat sink collects it, right? Your heat sink collects it. A sink, it's like a pool.
It's not a piece of metal that's there behind some of them electronics.
Yeah, to absorb heat, it's a sink, right? So the scope is a sink. So in your library browser, that's just the definition of the word library browser. You're gonna come down to sinks, and then you're gonna pick out the scope or display. So source is like the input, and a sink is kind of like the output. Okay.
So when you go in the library browser and you click on scope, it's supposed to show up, right?
When you go in live, no, you gotta drag it out.
Oh, okay.
Yeah, it's supposed to be smaller. Why is this in the? Yeah, library browser should be like this, and you usually like click on this and you drag it out. Yeah, so the guy about this square wave, if you want a perfect square wave, you can use this pulse generator thing, right? You can go inside, you can change the period, right? We know our simulation time is about 10 seconds, so we just want a few pulses in there, so we just change the period to 2 seconds. And the pulse width for a square wave, we would want a 50% duty cycle. Duty cycle is something you would learn in electronics and stuff. Right? Click apply, you run, and you would get a perfect square wave. So if you wanted a perfect square wave like this, right, you can just go ahead and use that pulse generator to generate that perfect square wave. This here is just an exercise to break down the square wave. So here, of course, these square waves don't match because they have different frequencies. And so I would have to change the period to something like 2 pi, I guess, would be the period. Yeah, 2 pi. For these to match up. Okay, so this here is a square wave. We'd have to shift it down a little bit and change the amplitude to 2. Change to 2. Then we'd have to put a constant in here, right? So constant. Okay, good. So if you play around a little bit with your pulse generator, you can generate the same square wave we're going after, right? In our scope. So this is a square wave we're kind of going after, right? It's well-defined one. And this here is the ideal square wave that comes from the pulse generator. So you can play around with your pulse generator, set up this circuit, right? And then get your ideal square wave. I'm not sure.
Excuse me, sir.
Yeah.
It's still not running. I don't know. Maybe I'm making a mistake somewhere.
Oh, share your screen. Let's see. So maybe your computer is a bit slow. Could be. Right. Did you try running it before?
Not really. There it is. I don't know if you can see it.
Okay, let me stop sharing mine.
It's visible.
If that's wrong, no, you need to click on the scope.
On the scope, this one.
Yeah, double click on it.
Sir,
Oh, you need to double click on it.
Yeah, so what you're outputting, you need to change the parameters of all the different sine waves, right?
Okay, I changed this one to amplitude only to be a third.
So the frequency needs to be changed as well, right?
Okay,
yeah,
I'll do
isn't
that.
the frequency for all M1?
No,
The
right?
first one alone. The first one, the amplitude is 2 and the frequency is 1, right? Sine wave 1.
No, no. Okay. Go ahead and stop sharing, Billy.
Okay, good.
Let me share mine again. Okay, no. Okay, no. Good. New. So, okay. A sine n of x, right? The n represents the frequency. The A represents the amplitude. So if you see something like sine 3 of x divided by 3, this is the same as 1/3 sine
Sine 3x.
sine
Yeah.
3x, where 3 is the frequency
Frequency.
and 1/3 is the amplitude,
Amplitude.
right? Okay. So this here at the top here in black, you guys can see this, right? This here is the function. And we want to add sine of x plus sine 3 of x divided by 3, right? Divided by 3 here, plus sine 5 of x divided by 5, plus sine 7 of x divided by 7, plus sine 9 of x divided by 9, and so on and so forth.
So hold on, sir. I understand the function then now, but the first regular one, what we without it being divided by anything, what was that? The basic amplitude was 2 and
1.
the basic frequency was
The
1.
basic amplitude is 1.
And the basic frequency is
1.
1 as well.
Okay, good.
Right? Okay, this is sine 1 dot x divided by 1. Divided by 1, right? We don't need to write that.
How do you change the input or the scope? Okay, for
Yeah, so again, clicking on the scope, double click on it, right? Up here, file, number of input ports, 3, right?
Oh,
3.
thank you, thank you, thank you.
Let me just get my charger.
So sine wave 2, the frequency is gonna be 3, right?
Yeah, the frequency is going to be 3 and the amplitude is going to be
Be a third.
1/3. Yeah.
Oh, okay, good. Yeah. Thank you.
Mhm.
Sir,
Yeah.
when I press run, it ain't showing up.
Click on the
What do I
scope.
do? You gotta click
Click
on the scope. Yeah,
Double
because
click
I
on.
tried it and then it came up. I just wonder if something's wrong.
No, you need to click on the scope to view it.
Okay, okay.
Hmm.
Okay, did everyone get this running?
I'm trying to remember how you increase the processing thing of the wave.
Yes, of course. Modeling, right? The solver, right? Modeling, model settings. Click on that. It's gonna pop up some stuff, right? In the solver, right? You're gonna see something like this, right? Start time, stop time, whatever, variable step, fixed step. You're gonna click solver details, and then you're gonna click max step size, and you can change that to 0.0. So this system is kind of like solving the system, right? It's gonna solve it at this time, then it's gonna solve it again, and it's gonna solve it again, right? It's gonna solve its store value, solve its store value, solve its store value. Right, so if we said the max step size is 0.01, every 0.01 seconds is gonna stop, solve the system, and store that value. Okay, it's a 0.01 in the max step size. Right, so solver details here. Max step size 0.01. Don't worry with everything else. So how many people finished with this? And they have not the perfect square wave, but they have something that's okay.
Sir, mine is only able to give a single wave on the oscilloscope. Sorry, the scope.
Yeah, so you click on the
Sir,
scope,
show back your wave.
click
Let me see.
file, and you click number of inputs here. So you can do 1, 2, 3, 3 inputs. That's what you're asking for, right?
Right, let me see number of input. Yeah, it's selected to 3, but only one wave in blue is showing. The rest are not showing up.
Oh, well, you need to add them into the scope. Let's say I want, right? Let's say I want this wave here. I can just click, like you click on the input, and then you click somewhere along the line to get this wave or this wave or this wave or this wave, right?
Okay.
So I click there,
so-
and now I need to run again, right? And again. And now you see I have that red wave there, right?
Okay, so what's the purpose of the sum again? Is it not supposed to sum all the waves because sine wave 1, 2, and 3 are joining into it and then outputting it to the scope?
So summing the waves, right,
Right.
is different from displaying different waves, right? So
Okay.
yeah, so it's like saying, okay, so 2 plus 2 is equal to 4. What the scope is gonna output, right? Remember, we sum this, right? Two
Right.
things come into summer, right? And then this goes out, right? So the scope is gonna display 4. It's not gonna display
It's
2
the output.
and 2, right? It's the sum of them, right?
Okay, so the
If
summation
you
of
want,
everything.
yeah. So if you want the individual waves, you need to come and pick them off, right?
Okay, good.
Come and pick them off.
All right, thank you, sir.
Because remember, it's the mathematical sum, it's the arithmetic, right? The functional sum.
All right, so second one. this. Project.
Sir,
Yeah,
how do you zoom out?
like zoom out to everything. You can just click this fit to view, and it kind of fits into everything.
Wait, the magnifier glass at the top right there, right? Top left, right?
That is zooming in. That was zoom in. Here,
So how do
it's
you zoom
to
out?
extents. Just click there, and you would zoom back out.
I click it, but like the page stick for the longest while. So I don't know what's going on.
Is your computer frozen?
No, it's not frozen, but they got a circle thing going in a circle like something loading, and it was like that for the longest while up to now.
Yeah.
It's low. Sir, for clarification, one more time, sir. The first
Yeah.
one is sine x. The next one is sine 3x divided by 3. The third one is sine 5x divided by 5. And the fourth one
Yeah.
is sine 7 divided by 7.
Yeah, look there right up here.
And why you have a fifth one up there? You have sine 9 divided by 9. Sine 9x divided by 9.
If you want to add more, you can.
Oh.
This is pretty ambitious. This is for the ambitious. If those that want to add more, they can.
So let me see what the waves look like again.
Remember, it's not going to be a perfect square wave. We're going to need to keep adding and adding and adding, right? In order to get a perfect square wave.
Okay, I have two. I don't have the perfect square wave, but I got two waves that's similar to the blue, and one like the red.
Okay, good. This perfect square wave comes from the pulse generator, but the blue and the red is where you need to have.
So
Good.
how did you add in that square wave, sir? What is it particular
How did I
box
get the square wave in? The ideal one?
pulse? Yeah, how did you put the pulse in?
Okay, good. Let me talk about that. So everyone's done with all this sine wave stuff, right? Let's just assume everyone's done. Okay. So now, as I said before, in Simulink, there are a lot of different tools, right, that vary according to all sorts of different fields and different field. And as this is probably something you notice when downloading MATLAB and Simulink, you had a lot of different toolboxes you could check from, right? Different things like robotics, antenna design, all these different fields, right? And with them come different blocks, right? Different blocks, you might want different things in different fields, right? Certain functions relate only to certain fields. Now, the pulse generator is a block, is a particularly common block, right? Pulse generator. It's called generator. Generator. And it does, as its name suggests, it generates pulses. Pulses. Now those pulses, and this is something especially true for digital electronics people that know about digital electronics. So when you guys learn about that, you learn about different pulse waves and different things, right? So essentially a pulse is just a modified square wave. So here would be 0, and it pulse up to some particular amplitude like 1. Right? So it'd be 0, pulse up to 1, 0, pulse up to 1, 0, pulse up to 1. And it will have some kind of defined period t, right? Some defined period t, and here would be some kind of width, right? Some kind of width based on the value of t, right? So it'll be W divided by t, but expressed as a percentage, right? So something like a 50% duty cycle would mean that this thing was on for 50% of t, right? Let's say t was something like 10. The width would be 5, right? 50% duty cycle. 5 divided by 10, right, is 0.5, which is 50%, right? That's how much it was on. And we can change it to, of course, 30%, 70%, whatever, as we vary the width and the period, right? Now with our square wave, right? Square wave is not a pulse wave, it's a modified pulse wave, right? With the square wave, we have our 0 line, right? Square wave comes, it goes up to 1, comes down to -1, it goes up to 1, it comes down to -1. So there's 1 here, 1 here, -1, right? Here is some period t, and here is half of t, right? 50%. So the square wave, the duty cycle is 50% for square waves. Now the amplitude, right? The amplitude here to here, right, would be 2, but 2 shifted downwards, right? Shifted downwards. Now, from signals and systems, which is just a thing where you analyze functions, we know that if we took a pulse wave with a pulse generated wave with amplitude 2, and duty cycle 50%, and we shifted it down by 1, right, we would get this square wave, right? So imagine,
Sir,
yeah, just give me a second, let me finish my thought. So imagine if a pulse wave was up here, use a different color. Okay, so imagine if a wave was here, pulse generated wave, going up to 2, coming down to 0. Up to 2, coming down to 0, right? Here at the value of 2, but we shift it down, right? We slide it down. it would line up with this sine wave, right? It would line up. It would line up. If we shift it down, right? It would line up with this sine, with this square wave, like this, if we were to shift it down. Right? If you can see that happening. So mathematically, we kind of need to subtract 1. Let's look at Desmos, right? Let's say we have sine of x, right? This is this way. Let's zoom in a little bit, zoom in, right? Sine of x. If we add 1 to sine of x plus 1, and it goes up 1, right? Remember sine of x, start at 0 here. If we add 1 to that, everything goes up 1, right? If we subtract 1 from that, everything goes down 1. So adding shifts allows us to do that shift. So if we can generate a pulse wave with duty cycle of 50%, right? 50%, which is half and half, half and half, and an amplitude of 2, remember, pulse starts at 0 and ends at the amplitude, right? And we shift it down, we would get this square wave. Yeah. Now I'm sure there's some square wave function along the way, right? But this way allows you to play with more blocks, right? Good. So what I have here is a pulse generator with an amplitude of 2, right? With an amplitude, don't worry about the period as yet, and a pulse width percentage of period at 50%, right? A pulse width of 50%. Okay, right? So amplitude 2, duty cycle 50%, and then we subtract 1 from it, allowing it to be shifted down, allowing us to get this. Now, another thing we need is the period as well. The period is 2 pi, right? Because these sine waves are in radians, and the period of the sine wave is 2 pi. So in here, we have amplitude 2, period 2 pi, pulse width 50%. Okay, good. So now, are there any questions on this?
Yes, sir.
Okay.
Sir, how do you get the constant?
A constant. So you double click at constant and here, right? Constant.
Thank you.
Okay. You can also just go library browser, right? Sources, and in here should be a constant, right? The second row, constant. Constant, the 4th item, constant. There are also some other things, right? Random numbers, right? If you want to generate a random number, there are all sorts of different blocks, and you guys can play around with it, right? There's also the step function, which is useful sometimes. Yeah.
Sir, can you go back to how you got the properties of the pulse generator? Because right now when you right click, left click, I mean, yeah, right
double click on it, double click on it, double click on it, or you right click, block parameters.
I don't know about it.
Block parameters. So you either double click or you right click block parameters, right? And the parameters are amplitude of 2, period 2 pi, pulse width 50%. Okay?
Sir,
Yeah.
could you please go back the calculation for the pulse generator? And also, do we now need to put a pulse generator inside the circuit that you show us?
Yeah, this is the pulse generator, right?
No, is this just showing me for information, or we got to put it in?
You put it in practice, for practice.
Okay. So should I just create a 4th port and put it in, or change it up like how you change it up here?
Whichever way you want to do it.
All right, just making sure.
You're given
And
creative
the calculations, sir.
Okay,
The
yeah.
calculations, sir.
Okay. So the square wave we want, starts at 1. Let me change this to black. Starts at 1. Starts at 1 and it goes down to -1, right? This here is our 0 line, 0. Right, so it's kind of like this, going up to 1, coming down to -1, going up to 1, coming down to -1, right? The period is 0 to 2 pi. We know this from our sine wave, right? The sine wave we're using, the period of those sine waves is 2 pi. Yeah, at least the base one. The first one that we're using to add all the other signals on top of was 2 pi, right? 2 pi. We know that. So for the period, we're going to use 2 pi. Now, in the pulse generator, remember that goes from 0 to 1 or whatever its amplitude is. All my writing is kind of twisted for some reason. That goes from 0 to 1 or its amplitude, right? Its amplitude. So if this amplitude was 4, it would have gone to 4, right? So the thing is, what we want to do is set our amplitude to 2, right? Set our amplitude to 2 and shift it down. So this would be our square wave. Our square wave, right? Our pulse generated wave would be something like this, going from 0 to 2, right? To 2. But if we shift it down, right? Shift it down, it's gonna come and fall into, it's gonna come down from there. And we're shifting it down, right? We're shifting it down and it's gonna fall into place here. Right? So that's why we need to shift it down by 1. Right? We need to line this 2 up, this peak here, with this peak here, so that this bottom peak here would line up with this bottom peak here, right? So we need to shift it down by 2.
So
And
hold
that's
on, sir,
why
wait.
we got this -1, right? So in your summer, remember 1, those need to be a minus sign, right? So we need to subtract 1 to shift it down. As I was saying, with the sine wave, right? There's the regular sine wave. It's a 0 here. We add 1, it shifts up, right? We subtract 1, it shifts down. Okay, so our pulse generator, right? Remember, it starts up at 0 and it goes to 1. All right, let me just do this in MATLAB. Let me remove the line from the scope. Let me connect this up to here, right? So we can see both, and let me run it. So if we look at this scope, we see here, this is the original wave, right? In the blue. And by adding this constant 1 here, right? We shift it down to this level, right? Which is the
So
level
why do we need to shift it down, sir?
because we want our sine wave, right? We want it to be close to the non-ideal square wave we're generating. Right? So this is our non-ideal square wave, and we want it to represent the ideal square wave that we're chasing after. Make sense?
Like, why can't we just change amplitude of the square wave to 1 instead of putting in a constant?
No, because remember the pulse generator, right? The pulse generator goes from 0 to its amplitude. It doesn't start from -1.
So
right?
it starts at 2. It always starts at 2.
No, we put it to start at 2 because we want to start at -1. All right, let me one more time. Okay, so the square wave is at here. 1 minus 1, right? The square wave is here. The pulse generator goes from 0, right, to amplitude, whatever we set amplitude at. If amplitude is 1, it's going to go from 0 to 1. We want it to be here. Right? Distance between 2 points is 2, right? From 1 to minus 1 is 2. This goes from 0 to amplitude. It's always going to be 0, right? So if we want it to be the same length as this, we need to change amplitude to 2, right? So that's going to be that same length. It's going to go from 0 to 2. Then we need to subtract 1, not from the length, not from this distance, but subtract 1 to shift it down, right? Shift it down so that it'll be here, 2, it'll be 2, and this 0 is going to shift. Now 0 minus 1 equals minus 1, right? Is going to become minus 1, right? And this here, instead of being 2, here is going to be 1, right? Because the pulse generator starts at 0, right? Make sense? Pulse generator always starts at 0.
All right, sir. Okay.
You understand, or are you still confused?
I'm a little bit clear, but I don't understand fully. But I kind of get what you're saying a little bit, how the pulse generator doesn't come out at 2, but you want to shift it down at 1. So it looks like the ideal sine wave you're trying to generate.
Yeah,
And you got to put a constant in there to shift it down by 1.
Yes, good, good,
Okay.
good, good.
So wait, so the constant value is 1.
Mhm.
So
So
the
remember,
pulse generator value is what? 2?
2. So remember, this is 2 to 0 to 2 to 0, right? But we subtract 1 from down here. So here, when it's 0, we're going to subtract 1 from 0, and it's going to be minus 1.
Minus
right?
1.
So 2 is going to be 1 and minus 1. 1 and minus 1. Say, you get it now?
I get it. I get it.
Good, good. So I can go ahead and delete this line. Right. Okay, okay. Right. And this is just to play around with functions and get you guys accustomed to the software, right?
Excuse me, sir.
Yeah.
The -1 that you're demonstrating on the Desmos, it's kind of the Y-intercept, right?
Yeah, kind of like that. Yeah. Okay, so
Oh.
Y-intercept is like for a line, right? So 5x, right? 5x. And then here is 0, right? So if we do plus 1 at 0, it's actually going to be 1, right? If we do minus 1 at 0, it's going to be minus 1. So it's kind of like shifting it, right? So let me draw the 5x again, right? And let me do 5x. Let me remove that sine wave. So if we zoom in, you see it's kind of like shifting it up and down, yeah? Shifting the line up and down. So with the sine wave, right? Sine of x, sine of x plus 1, we see, zoom out a little, it's like shifting the sine wave up and down, right? So for a square wave, it's going to be shifting it too, right? So the middle one is the main one, and we shift it up with plus 1, right? Plus 1, or we can shift it down with minus 1.
Right.
Yeah, good. So essentially that's what we're doing with this constant, because the pulse generator starts at 0 and goes up to whatever amplitude. So we can set that amplitude to 2 and shift it down so we get that 1 minus 1 thing.
Right.
Good. So I'm sure there's a square wave function, square wave generator right here. And we can click on its amplitude frequency, 2 pi, right? We can send that in. We can run. it is a square wave generator here in this blue, but we need to change the frequency, right? The period frequency is going to be 1. So we run that. We need it to start at 0.
Excuse me, sir. So the scope is kind of divided. The segments are kind of put in a similar fashion as the what do you call the thing? Cartesian plane, right?
Cartesian plane. Yeah,
Right,
yeah.
It's kind of. Okay, good.
It's the same way we would display multiple, like in this graph or calculator here, Desmos. It's the same way how this does sine x, sine x, whatever. This here does whatever we put into. We put in this is gonna display them in the same way, right?
Okay, good. Yeah, now it's more clear.
Yeah. Where are you from, Billy? You from?
From Africa, Kenya.
Okay. Which part?
Right. East Africa, Kenya.
Oh, what language do you guys speak there?
Swahili.
Okay. All right.
Right.
So how did you end up deciding to come to Guyana? How do you make that decision?
So it's a hell of a story. I wouldn't want to talk about it here for everybody to know.
Yeah, it's fine. If you don't want to.
Okay, good.
Yeah, but it's good that we get like a few international students. Oh, there's usually like some few Spanish students, like Venezuelan, maybe like 1 or 2 Jamaican or Trinidadian students. Yeah. Okay. So I think after that we can call it a day. After you guys figure this little pulse generator thing out, get it working, we can call it a day. Right? And you can go ahead and save your work, right? When you close it, they'll ask you to save, right? Or you can come to the side and click save. Right? You pick a name, right? You save it on your desktop. I probably save it in courses, right? Simulations, right? I'll do square wave, class, test, right? Right? And you can save it. So you can save your work, right? Now,
So we click on save as.
yeah, just click save. In the same way you save everything, save, just click save. And if you haven't saved it before, it'll ask you to save. If you've saved it before, it'll just update the file, right?
Sir, must please put up the recordings, right?
Yeah,
this-
yeah,
this
yeah,
class.
yeah, sure. Right, and I'll email you guys the link.
Okay, sir, thanks.
Yeah, and you guys can come in, right? Play around with examples. Right. Some might be useful, some might not. Right. Play around with examples, see what looks fun, right? And of course, online. Simulink examples, right? Like a lot online, yeah. Right, there's like way more than what is displayed, you know, on your desktop. It's like a lot more. like a double spring mass, all sorts of things, right? Like missile guidance system, 2 bouncing balls instead of 1 bouncing balls, hydraulics in their simulations, right? Loading a tank, all kinds of different things. Just like designing missile guidance systems. There's a cool one, right? View MATLAB command. You can just come here. Like, let me send you guys the link to the examples in the chat. Okay. All right. So this is the link to the examples. So you can go through, look at them, right? And then when you click on them, you come to the right hand, you click View MATLAB command. It's going to have this command here, right? So you copy that command. You come into MATLAB, you paste that command, right? Which essentially just said open this example, right? Nothing fancy about it. Open that example. And then you'll have this fancy system. Remember, Simulink isn't something graphically intensive, right? It's more about the data, but this one has a little bit of graphics, right? You load up, see some animation thing running. And you can try and figure out the math a little bit if you want, right? To see with your missile and it's doing its little guidance thing. And at the end of that, this is where we really care about all the different data, the positions, right? The acceleration, the incident angle, different things, right? Mach number, different fluid mechanics kind of thing, right? Of course, you'd have to learn a lot of mechanics and control systems to really understand what's going on. Okay? But what I want you guys to do is just pick an example and an example that interests you and look at it, see how Simulink is actually able to simulate this and help you in the design of this system. Right, so scroll through the examples, see which ones you like, and have a look at them.
So what this is for what? What do you want us to do?
So I sent you guys a link in the chat.
Yeah.
Click on one of the examples that you think looks cool and look at it, look at the different blocks they use, right? Play around, run it, see what's happening, right? Just for homework, so you guys have experience. All right? You understand?
I'm gonna check it.
Good. Yeah, it's just something to play around with,
I
right?
was focusing on my program, so that's why.
Okay. Yeah, just click the link and explore some examples. Hopefully learn something. All right, good. So that's all I have for you guys. As long as you finish with this, you guys can go ahead and leave. Enjoy the rest of your day. Enjoy your Friday. And I'll see you guys next week, Tuesday. All right, good. That's the end of class.